In this example, we're told we have a standard Otto cycle with a compression ratio of 10, and we're given some information about the initial state of the cycle. We're also told that the mass of the air in the Otto cycle and the maximum temperature of the cycle. So then we're asked to find the heat rejection. Let me highlight this. Heat rejection, the net work, thermal efficiency of the cycle, mean effective pressure, and the TS plot. So let's go ahead and just sketch out what this looks like. We have a piston cylinder sort of arrangement. So here's piston, here's the cylinder, there's air in here. This is our system of interest. Of course, the piston moves up and down. Let me go ahead and sketch out a TS plot just qualitatively here, and then we'll work out the details in just a moment. Okay, so we're told the initial state, state 1, we're told that the pressure, so 100 kilopascals absolute, and we're also told T1 is 27 degrees Celsius, which we'll go ahead and convert over to Kelvin. It'll be 300 Kelvin. All right. We're also told, let me just make a note here, that the mass of the air is 5 grams. So that's 5 times 10 to the minus 3 kilograms. And we're also told the maximum temperature of the cycle, that'll occur at state 3. So let me sketch this out on a TS diagram. So state 1 would be here. During the compression stroke of the Otto cycle, we have isentropic compression. So that means that we head this way to state 2, so that's the compression stroke. From state 2 to state 3, that's the constant volume heat addition. So what we're going to do is move along a line of constant volume here. So this is V2 is equal to V3. It's a constant line to state 3. Right, so this is a kind of it's called an isochoric line. It's a line of constant specific volume. That's where the heat addition is coming in from 2 to 3. From 3 to 4, that's an isentropic expansion. That's the power stroke. And then from 4 to 1, that's a constant volume heat removal. So that's what our Otto cycle looks like. And so you can see very quickly that T3 is our highest temperature. T3 is, we're told, 727 degrees Celsius, which comes out to be 1000 Kelvin. So that's our highest temperature in the cycle. All right, so let's try to figure out the properties at our various states. So at state 2, we can determine what's happening at state 2 here by noting that this is a constant entropy compression process. We're dealing with air as an ideal gas, so we're assuming that air is an ideal gas, and we have a constant entropy process, so that means we can use relative volumes to determine the the state at state 2. So if you recall, the way we use relative volumes is we have the volume at 2 over the volume at 1. It's the same thing as having like the specific volume at 2 and the specific volume at 1. That's because the mass remains the same. That'll be related to the relative volume at temperature T2 to the relative volume at temperature T1. Remember that those relative volumes, you can only use those for an isentropic process involving an ideal gas. Okay, so we can rearrange this to find the relative volume at T2. So we'll just do a little rearranging. Okay. So as far as the relative volume at T1, we can look that up in the ideal gas table. So if you go back up to state 1 and you use the ideal gas table, you'll see the relative volume at T1 comes out to be 621.2. This comes from the ideal gas table. And then, so we know that value down here, 621.2. The V2 over V1 comes from the compression ratio. We're told that the compression ratio is equal to 10. So the compression ratio we typically give as being related to the symbol R. This is actually 1 over R, because the volume at state 1 is bigger than the volume at state 2, because it's being compressed. So remember, just the compression ratio is defined as V1. That's the volume at the bottom dead center to V2, which is the volume at the top dead center. Okay. So down here, this is just 1 over the compression ratio. So we know that that value is equal to, the compression ratio is 10. So we can then find VR at T2. That just comes out to be 62.12. And then we can go back to the ideal gas table to look up the value for T2. So that comes out to be 730 Kelvin. And we're going to be using specific internal energies in this problem, so I'll look that up while I'm there. That's 536.1 kilojoules per kilogram. Again, these come from ideal gas table. By the way, up at state 1, while we're looking in the table for the specific, for the relative volume there, we could also look up the specific internal energy for that, and that comes out to be 214.1 kilojoules per kilogram. All right. We could also use these relative volumes to figure out what's happening from state 3 to state 4, because again, we're dealing with an ideal gas, and this is an isentropic process. So we could use the same idea going from volume 4 to volume 1. We're just making use of these relative volumes because it's an ideal gas undergoing an isentropic process. I'm sorry, that should be a 3, not a 1. All right, and since we know that the temperature of 3, we're given that, so we can find the VR3, the relative volume at state 3. We also know that the volume at 4 is the same as the volume at 1 because this is a line of constant volume, so V1 and V4 are the same. We also know that V3 and V2 are the same, right? So we could make use of that information to solve for what the temperature is at state 4. So let me rearrange this. Okay, so as I mentioned before, that we can look up in the ideal gas table to find that that comes out to be 25.17. And then V4 over V3 will be the same as V1 over V2, right? And that will be the compression ratio. So that's just equal to 10 in this particular case. So then we'll see that VR at T4 comes out to be 251.7. So then we can go back to the ideal gas table to get that T4 comes out to be 430 Kelvin. And again, while we're there, we'll look up the value for the specific internal energy. That's 308.0 kilojoules per kilogram. And one other quantity we'll want is the specific internal energy at state 3. So since we know that T3 was the 1000 Kelvin, that was given in the problem statement, again, we can use the ideal gas table to get U3. And when we look that up, that comes out to be 758.9 kilojoules per kilogram. So what we've done so far is just we're finding properties at all the various states. What I'm particularly interested in ultimately are the specific internal energy values. We've gotten U1 there, we have U2 here, we looked up U3 given T3, and then we also found U4. We're going to use these because we're going to calculate the value of work and heat using the first law applied to the various parts of this cycle. Okay, so we've just found properties at the various points so far. So now what we want to do is find the heat rejection. I don't know why I put rejections, but heat rejection. So that occurs from 4 to 1. That's when we're dissipating the heat to the environment. So we'll apply the first law to the air as we go from 4 to 1. And what that will look like is when we work it all out. Let me just write it out and then I'll describe it. It'll look like, let me just double check. Yeah, it'll look like this. Okay, so what I've done here in this expression, this is the first law. On the left-hand side, I've neglected kinetic and potential energy changes. Okay, so no change in kinetic or potential energy. That only leaves changes in internal energy. On the right-hand side, I don't have any work because it's a constant volume process. If you look from 4 to 1, you can see that the specific volume remains constant. So remember, it's a constant volume heat rejection. So there's no work there's no PDV work, so that's why that doesn't show up. And then the only other thing is I wrote it in terms of Q out rather than Q in, so that's why I have a negative here, Q out, just because I know the heat's going to be going out. So I can plug in my values for U1, U4, I'm given the mass, and then I can solve for Q out. So when I solve for that, ultimately that value comes out to be, let's see if I've got it written down here. I know I've worked it out. Just give me a moment here. Okay, here we are. Should be 0.470 kilojoules when you work out the numbers. So that's the heat coming out of the system. Okay? So that's part A. Now part B is find the net work in kilojoules. So the net work, there are two places where work is occurring. From 4 to 1, there's compression. I'm sorry, not from 4 to, from 1 to 2, that's compression of the air, right? So that's the isentropic compression. And then from 3 to 4, there's work being done by the air. So that's the power stroke. So if we want the net work, we're going to have to apply the first law from 1 to 2 and also the first law from 3 to 4. So let's do that. So if we write this out from 1 to 2, it'll look like the following one. Okay, so this is the first law applied from 1 to 2. That's an adiabatic process, so there's no heat transfer. And again, we're neglecting kinetic and potential energy differences. So we know all the values for the internal energies and the mass, so we can calculate W dot in. So this is the isentropic compression of the air, so the work is going in. And that comes out to be, let's see if I've got that written down somewhere here. So this is from 1 to 2. It doesn't look like I actually calculated this one. I apologize. I don't have the number handy at the moment, but we could calculate that value. I'll show you why I didn't do it in my calculations. We'll come back to it in a moment. So this is going from 1 to 2, and then we'll do it from 3 to 4. We'll apply the first law. It'll look like that. This is, again, first law from 3 to 4. This one, since I know this is the power stroke and the power is coming out, this is why I have the minus sign. Again, it's adiabatic, so there's no heat transfer. So this one, let's see if I've got that one worked out. And it looks like I didn't calculate that one either. So I apologize for that. But you can plug the numbers in. They're all right up here and calculate those. And I'll show you why I didn't do that in just a moment. Lastly, let's figure out the heat transfer that occurs from 2 to 3. This is the heat addition up here from 2 to 3. It's constant volume heat addition. That's mimicking the combustion process. So let's do that one. Okay, so this 2 to 3, we do the first law. Oops, it's not 4. That's constant volume process, so there's no work being done. So you can plug the numbers in here. And that one, I do have the numbers for that. That comes out to be 1.11 kilojoules. So remember that what we're ultimately trying to get is the net work out of the cycle. So if I apply the first law to the entire cycle, right, I'm applying it to the air over the entire cycle. Remember that over a cycle, the properties don't change. So the change in the internal energy over the cycle would be 0. So if I do the first law over the whole cycle, what we're going to get is this left-hand side. This would be the change in the internal energy of the whole cycle. That's 0. And then we're going to have the heat coming in. So that'd be Q in from 2 to 3 minus Q out from that would be from 4 to 1, plus the work being done on the air from 1 to 2. Let me put that as W in 1 to 2 minus the work coming out from 3 to 4 during the power stroke. So you can see then that W out 3, 4 minus W in 1, 2. This is the net work out, right? That will be equal to Q in 2, 3 minus Q out 4, 1. So I can find the net work out by just taking a look at the heats. So that's why I didn't, in the solution that I'll post, I didn't actually calculate these values because I ended up using the heat. So I do know the Q in is 1.11 kilojoules, and I know the Q out is 0.47 kilojoules. Make sure I got the numbers right. Yeah. So we can then find the net work out. And then that value comes out to be 0.645 kilojoules. So you can find it different ways. So in the solution I did, I based it on this kind of applying the first law over the whole cycle to find the net work out. But another way you could do it is you could have found each individual work component and then just subtracted them. You should get the same result. All right, so then that gives us part B. Part C is to find the thermal efficiency of the cycle. So the thermal efficiency of any power cycle is going to be the net work out divided by the heat that's been put in. Not the net heat put in, just the heat put in. So this will be the net work out, and the place we're putting in heat is from 2 to 3. That's the combustion part of the cycle. So we know those values. So this is 0.645 kilojoules, and the heat coming in was 1.11 kilojoules. So you can calculate the efficiency from that, and that value comes out to be 57.8%. All right. The next part of the problem is to find the mean effective pressure. That just, all you have to do is remember the definition of the mean effective pressure. So the mean effective pressure was defined as the net work out divided by the displacement volume. So the displacement volume would be the volume at state 2, the volume at state 1 minus the volume at state 2. Because my cat's making noise in the background. It's her time for her to eat lunch, and she's letting me know. Okay, so anyway, the displacement volume is the volume at bottom dead center minus the volume at top dead center, so that'd be V1 minus V2. So let's write that out. Again, this is volume bottom dead center. This is the volume top dead center. And I believe we calculate, so we know that from the compression ratio, we know that the I'm just trying to see what I had calculated here. Yeah, we know that V2 should be 1/10 the value of V1 from the compression ratio, right? So now what we need to do, we know the net workout. Now we just need to find the volume at 1. We can find that from the ideal gas law at state 1, because we know, and from the problem statement, we know the temperature at 1, we know the mass of the air, and we also know the pressure at state 1, and we know the gas constant for air. So if you plug in those numbers, you'll find the value for V1. So let's see what that is. That comes out to be 4.31 times 10 to the minus 3 cubic meters. We can substitute that in to get the mean effective pressure. 166 kilopascals. All right, so that part of the problem is just really just knowing the definition of the mean effective pressure, knowing how to find V2. That just comes from, remember that V2 is just 1 over the compression ratio times V1. And then finding V1 from the ideal gas law. So what we've done in this problem is we've found the mean effective pressure. We found the thermal efficiency using our standard approach. We found the net workout using standard first law analysis. There are a couple of different ways you could do it. You could either look at the whole cycle and then calculate the heat transfers, or you could just do it for each component or each process in the whole cycle, which is the way I started it here, but didn't work out the numbers. The last thing we're asked to do in this problem is to sketch the TS diagram, which is what I've done here. All right, I think that covers everything in this example, so we'll go ahead and end it there.